Hi, and welcome to Section 3.5, Related Rates, also known as some of the most exciting application problems you will probably see up to this point in your math life. A lot of times when you are doing applications, a lot of you have been able to just kind of look at the problem and figure out what the answer will be in your head. These types of problems don't work like that. It's really important that you have proper notation so that you can find where you need to put things and follow your work and do substitutions correctly. So there's some guidelines for solving these. First of all, draw a figure if necessary and choose variables for all unknowns. With these problems, you'll usually have several unknowns, and you want to make sure that you understand what each of those stands for. Write out what's given and what is to be found using your variables, and with this, we have our dt symbols. So that's going to be the notation we use in this particular section. Instead of just saying y prime, we're not going to do that for this particular section. We're going to denote that we're taking the derivative of whatever variable with respect to time. So all of these derivatives are going to be with respect to time. So you'll be using, say it's area, you'll do dA dt. If it's volume, you'll say dV dt, so the derivative of volume with respect to time. And whenever it says the rate of change, that's talking about the derivative. You're going to write an equation that relates the variables. If the quantity is changing, it must be represented with a variable. So if it's changing, it needs to have a variable associated with it. If it's constant, you're going to put a numerical value. And you'll typically have two equations. One's going to be a primary equation. That's the thing that's having the rate of change happen to it. And one will usually be kind of like a helper equation. So you'll have a primary equation and a helper equation. Once you take your derivatives, you're going to substitute values in and solve for your unknown. So there's several formulas that you're going to need, and these need to be memorized. These will not be given to you on the test. It's something that you need to know. So you have your right triangle, we have Pythagorean Theorem, and the area of a triangle. Circle, we have area and circumference. Volume for a sphere and area for a sphere are given. For a cube, we have our volume and area. And cone, we just have volume. And rectangle, we have area and perimeter. So please, please, please work on memorizing these formulas. All right, so let's start. The first problem we're going to look at already has 3 of the first steps done. We're just seeing how to complete the last few steps, kind of building up to a main problem. So we're given that the area is s squared and that ds dt. So ds dt is the rate of change of the side with respect to time. And then we want to find, let's go to writing on this. Okay, we want to find dA dt. So the rate of change of the area with respect to time if our side length's rate of change is 3. All right, so we know what we're given, and we know what we have to find. So we're going to go ahead and take the derivative of our primary function. So our primary function is a equals s squared. So if I'm taking this derivative, it's important to remember you're doing your derivatives with respect to time. So t is is our variable. So the derivative of a is 1, and then we're saying we're doing the derivative of a with respect to time. It's sort of similar to when we did implicit differentiation. Whenever we took our derivative, we had to put that y prime on there. This is similar to that, but we're saying we did the derivative of a with respect to time. So dA dt is equal to the derivative of s squared is 2s. So the variable that we worked on was s, so we say ds with respect to time. So we have dA dt equals 2s over ds dt, or times by ds dt, sorry. All right, so remember that we are trying to figure out what dA dt is equal to when the rate of change of the side length in relationship to time is 3, and then at the specific moment when my side length is 4. So we're going to plug these values into dA dt. It's important that we wait and plug these values in at the end. Plug values in at the end. The reason this is important, if you plug your values in from the beginning, it takes away the variable, and then we would just be taking the derivatives of constants, and the derivative of a constant would just be 0. So we have to wait until the end to plug in part of the givens. So dA dt equals 2. So we're trying to find the rate of change of the area with respect to time when our side length is 4, given the rate of change of the side with respect to time is 3. So this is going to be 8 times 3. So our average, or not our average, but our dA dt, or the rate of change of the area with respect to time when the side length is 4 is 24. All right, so example 1b. Let's look at what we are given. Dx dt is equal to -6, y is equal to 4, and we are given a product of x times y equals 12, and we need to find dy dt. All right, so looking at this, we need to find something to take the derivative on. So we're going to start with our equation x times y is equal to 12. If I try to take the dy dt of this y equals 4, that's just a specific constant, and the derivative of that would be 0. So we're really not going to get anywhere with that. So it's kind of like they wrote these backwards. This is our final pieces of information that we're going to plug in after we derivate this equation. All right, so when I take the derivative of xy equals 12, we have to remember that our variable is t. So using the product rule, we have the first times the derivative of the second. So the derivative of y is 1, but we have to state we did the derivative of y with respect to t, dy dt, plus the second times the derivative of the first. So the first is x, the derivative of x is 1 times by, since x isn't our main variable, and t is, we have to state we did the derivative of x with respect to t. So dx dt equals the derivative of 12. 12 is just a constant. That's going to give us 0. So the thing that we are trying to find, again, is dy dt, which you can see is right here. So now that we've taken our derivative, we can substitute in y equals 4, which was given, and dx dt, which was given as a negative 6. So this would become, ooh, do you see a problem that we have? I have x, dy dt, y, and dx dt. And I only have y and dx dt. So I'm missing an extra value. So if I know y is 4, and I need to get x. Oops, I don't even want to erase all that. How could I use the information that's given so that we can plug everything in and only have one unknown? So I need a value for x, and I have this relationship between x and y. So using what was given, we can solve for x by substituting in the given value for y and saying, okay, when y is 4, x is 3. All right, so now we have enough information to plug in. This will be 3 times 1. dy dt is what I'm looking for, plus 4 times 1 times we were given dx dt. So plug in your negative 6 equals 0. And we're just going to solve for dy dt. So I have 3 dy dt equals 24. Divide by 3. And we get 8. Now, we weren't really given any units, so we can't label this right now, but usually at the end it's really important to label what you found. So let's go ahead and move on to example 2. All right, so in example 2, they're not starting us off with a couple of pieces already written down. We're going to have to find all the information that we need from the given problem. So a windlass is used to tow a boat to a dock. The rope is attached to the boat at a point 15 feet below the level of the windlass. So that's this length here. Oh, I'm not in drawing mode. Hold on. That is this length here, 15 feet. If the windlass pulls in the rope at a rate of 30 feet per minute. So the fact that it's telling me that this is a rate, they're giving me a value of a derivative. Okay? So we need to figure out how to label that exactly. But this is really important information right here. See if I can highlight it. So when it says at a rate, oh, I thought that would be a little bit thinner. Let's see. Let's fix this. Well, I'm not sure how to make it not cover everything up. But, so let's erase that. Maybe we can change our color a little bit. There we go. So make that red. Let's give this a shot. So it pulls in the rope at a rate of 30 feet per minute. So we have a rate of 30 feet per minute. That's important. Now, that's talking specifically about this rope, and that's labeled Z. So we know we have a dz dt. So we have the rate that the rope length is changing, and it says it's a rate of 30 feet per minute. Now, something that's important here is instead of just 30 feet per minute, we actually have to make this be a negative. So the reason this is negative is we have a decrease in Z. Okay, so length Z, this is decreasing the length of Z. So we use a negative. If our length was like, the boat was like kind of drifting out and increasing that length of rope, we would use a positive value. All right, let's keep reading. At what rate is the boat approaching the dock? So if we're asking at what rate the boat is approaching the dock, that is this length that's changing. So we're trying to find the change in x with respect to time. So we're given dz dt, it's a negative rate, and we're trying to find dx dt when x is, nope, I have to be careful here, it's not x. So it says when there is 25 feet of rope. So the rope is related to z. So that's when z equals 25. All right, so we are trying to find dx dt when we're given the rate of change of the rope is negative 30 feet per minute, and at the time when z is 25. So we need to come up with some equation that connects the unknowns in this problem. So notice I have an x and a z, and this would be kind of like our y, okay? The thing that I want you guys to see is that this is a right triangle. So what formula do we have that associates the sides of a right triangle? I'm going to go ahead and erase this just to give us some space. So right now we currently know we have dz dt is negative 30 feet per minute. We're trying to find dx dt when z is 25, and we need to use our formulas to connect the information together. So when you have a right triangle, we can use Pythagorean Theorem, which is x squared plus y squared, and we know y is 15 in this problem, equals, now how come I'm not putting 25 in for z? I put 15 in for the y, but I'm not substituting the value in for z just yet. If I substitute all of these values in to my equation, I'm just going to have constants, and I won't be able to, everything will kind of turn into zero. So the z is going to stay changing until we get to our actual rate of change. So we're going to derivate this with respect to time. Okay, so this is all related rate problems are with respect to time. Oh, it kind of timed out there for a minute and didn't keep everything on there, so I'm not sure what you can see. I hope you see x squared plus 15 squared equals z squared, and now we're going to derivate this. So when I take this derivative, the derivative of x squared is 2x. Now we have to hit that with a dx dt, because this is with respect to time. The derivative of 15 squared that's just going to be a constant, so that's 0, equals the derivative of z squared is 2z dz dt. All right, so we essentially have x dx dt equals z dz dt. So these twos cancel. We can just simplify that before we plug information in. Now that I have my derivative taken with respect to time, now I can plug in the given information, our rate of change of z and the length of z. To solve for, what are we solving for? Good thing I wrote it down. Dx dt. These problems can be kind of long, so it is really important that you write down information so that you can, number one, follow back to what you're looking for, and then number two, make sure you're putting it in the right spot. So if I were to substitute in dz dt and z, I would still have this x as an unknown, and dx dt is an unknown. So we need a little bit of help before we can actually finish this problem. So we know that y is constant. It stays 15. We are using x equals 25. We need to know what, I'm not sure if I said x, z equals 25. We need to figure out what x is. So we're going to go back to that Pythagorean theorem. So when z is 25, we have x squared plus 15 squared equals 25 squared. So x squared equals 15 squared is 225. 25 squared is 625. 625 minus 225 is 400. And we're going to square root both sides. Square root of 400 is 20. We don't want to do plus or minus here because we can't have a negative length for x. So we're just going to leave it at 20. So we're going to go ahead and plug in our negative 30 for dz dt, 25 for z, and 20 for x in order to figure out what dx dt is. So I'm just going to erase this for a minute. So we have x dx dt equals z dz dt. We found when z is 25, x is 20. We are trying to solve for dx dt when z is 25, and my rate of change of the rope is in negative 30. So dx dt equals, we'll divide that 20 off to get 25 times negative 30 divided by 20. So dx dt is equal to negative 37.5 feet per minute. Just checking to make sure I'm matching the units that were given. Okay, so what this means is that when the rope is 25 feet out, this length, the distance from the boat to the bottom of the windlass is changing at a rate of 37.5 feet per minute, and it's negative because this length, the length of x is decreasing, it's getting smaller. Okay. All right. Next question. Let's erase that. All right, final example. I think I can make, let's do, sorry, just trying to adjust my pen a little bit to see if I can get smaller. Nope, that made it a little bit bigger. Let's try one more thing. Oh, that looks better. Okay, let's give that a try. All right, so gravel is falling on a conical pile, so we have a cone, at a rate of 10 feet cubed per minute. So when I see the word rate, that means they're giving me a derivative. Okay, so gravel is falling on the cone, on a conical pile at a rate of 10 feet cubed per minute. So if the gravel is falling on top of this cone, it's making it get taller and taller and taller. So that 10 feet cubed per minute is increasing. I guess I shouldn't just say taller. It's kind of like that entire volume of the cone is increasing. So we're actually given dV dt. That's the volume, the rate at which the volume is changing with respect to time. So dV dt is 10 feet cubed per minute. Now, the fact that it said feet cubed tells me that I'm working with volume. So if my units are linear, I'm working with the rate of change of like a perimeter or a side length. If the units are squared, I'm working with the rate of change of an area. And if the units are cubed, that's telling me I'm working with a volume. So units are really important here to help you know what information you are being given. So I know that this is a volume because my units are cubed. Okay, so I'm given dV dt is equal to 10 feet cubed per minute. At all times, the radius of the cone is, so they're going to tell me about the radius. The radius of the cone is twice the height of the cone. So the radius of the cone is 2h. This is going to be kind of a helper piece of information that we're going to need to substitute in. Next sentence. Find the rate of change, so I'm looking for a derivative, of the height. So I need to find dH dt of the pile when the radius of the pile is 6 feet. So this is when r equals 6. And that's feet. Write a sentence explaining the meaning of the answer. Okay, so this is what's given to us in the problem. We know our volume's changing at a rate of 10 feet cubed per minute. We know that the radius is equal to double the height at all times. And we need to find the change in the height, the rate of change of the height with respect to time when r is 6. This is plugged in. These two pieces of information are plugged in last. Okay, those we don't want to end up zeroing those out. We need to use those in our final substitution. So right now, I only have this relationship with r equaling 2h, that's not doing anything that's not involving our volume at all. So we have to know our formula for the volume of a cone. Okay, so if we go to our formula sheet, our volume is 1/3 pi r squared h. This is the formula for the volume of a cone. All right. So let's go ahead and look at taking this thing's derivative. Now, if I leave it as is, notice that we have a product between r squared and h. We can avoid doing this product rule using the substitution that we know that the radius is twice the height at all times. So I can just substitute this into that volume formula and get 1/3 pi 2h all squared times h, which will give us our volume is 1/3 pi 2h squared is 4h squared times h. And if we simplify that, our volume would be 4/3 pi h cubed. This is a simplified form of our original using substitution of that constant relationship between the radius and the height of the cone. So this is what I'm going to take the derivative of. Okay, so let's clear this out. So I have my volume is 4/3 pi h cubed. So let's derivate with respect to time. So dv dt. This is just 4/3 is just a number, pi is just a number, so they are scalar multiples times by the derivative of h cubed with respect to time is 3h squared dh dt. Our 3's can cancel, and we have dv dt equals 4 pi h squared dh dt. Now remember, we are trying to solve for dh dt, the rate of change of the height of the pile when the radius is 6. So we have to think about substituting values in for dv dt. 4 pi is just a constant, and for h. So we know dv dt is 10, so we can go ahead and substitute 10 in for dv dt. 4 pi, now we weren't given h explicitly in this problem. All we were given is that the radius is 6. But we also know that at all times the radius is twice the height of the cone. So we can use that r is twice the height of the cone to solve for h. So 6 equals 2h, so h will be 3. So I can plug that into my problem for h, and remember that's h squared times by dh dt. All right, so we are trying to solve for dh dt. This whole piece is just a number. So dH dt is equal to 10 divided by 4 pi times 9, or 36 pi, which will reduce to, I am out of space. Let's see if I can erase something. Let me just erase this. There we go. So dH dt is equal to, we'll reduce that down to 5 over 18 pi. This is the rate of change of the height of the conical pile, the cone, when the radius is 6. So if it's just a height, if we're looking at the rate the height is changing, height is a linear unit, so this would be feet per minute. If this were, say, shrinking, if maybe there was like a hole in the bottom and gravel was falling out and the height was getting smaller, we would have ended up with a negative rate of change to indicate that it was shrinking. So the signs on these help you to know kind of if you're getting them right or not. If the whatever it is you're looking for the rate of change, if it's growing, getting bigger, it will be positive. If it's shrinking, getting smaller, it's going to be negative. These problems require quite a bit of work, and I hope that you can see from this just how important all of this notation is. You really need to focus on your notation, making sure that you have the equal signs where they need to go, stating the formulas, and putting those derivatives in this notation instead of just doing like a t prime. Okay. All right. We are going to work on this in class. I want you to watch this video, take notes, and try the homework. Our next class period will just be dedicated to working on related rates homework. All right. Good luck.